Look at this electric rickshaw. Vehicles like this dominate the low-cost electric vehicle market across the globe. To keep weight down and range high, they rely on energy-dense lithium battery packs. That energy density carries strict physical constraints. If a lithium battery is pushed past its designed voltage, current, or temperature limits, the chemistry destabilizes. The resulting thermal runaway is a self-sustaining chemical fire that cannot be easily extinguished. To prevent that scenario, these exposed battery packs are wired into a dedicated hardware component known as the Battery Management System, or BMS. It is the sole physical safety authority standing between the volatile lithium pack and the vehicle's motor. The BMS relies on microcontrollers and a network of sensors. It actively measures cell voltage, current output, and ambient temperature, enforcing strict physical limits by physically cutting power if a threshold is breached. A massive portion of these light EV fleets rely on hardware running the Jiabita, or JBD, and Xiaoshang BMS protocols. They hold a dominant market share globally. Instead of hardwired diagnostic ports, these systems are monitored and configured wirelessly by end users. The interface is a companion smartphone application, most notably the Android app BAT BMS. Recently, a threat intelligence report titled Operation Blueshock analyzed the BAT BMS application. It documented a severe flaw in how the app and the battery hardware communicate. The report details how obtaining unauthenticated digital access to these specific battery systems translates directly into the ability to execute kinetic physical sabotage. This diagram shows the wireless communication layer. The smartphone physically links to the BMS hardware via Bluetooth Low Energy, or BLE. The connection starts with the discovery phase. To identify itself to the phone, the BMS constantly broadcasts a single fixed BLE service UUID, 0000FF00. Inside that service are hard-coded characteristics. The battery uses a notify channel ending in FF01 to send data out and a write channel ending in FF02 to receive incoming commands. The vulnerability lies in the security gating of this connection. The protocol demands zero pairing, zero bonding, and zero mutual authentication to establish the link. A threat actor attempting to access the battery does not need to steal user credentials. They do not need to clone a paired device. The precondition is identical to the sequence used by a legitimate owner. Stand within 30 meters, scan for the fixed UUID, and connect. The engineers designed the hardware with the assumption that a Bluetooth connection was a secure internal vehicle bus, rather than an open radio frequency accessible to anyone nearby. This schematic details the proprietary byte frame format. Every time the app sends an instruction to the BMS, the data is structured exactly like this. The packet begins with a standard start byte, hex DD. This is followed by the mode byte, where hex 5A tells the hardware that a write operation is incoming. Next are the opcode, the length integer, and the payload section. This is where the actual vehicle commands and configuration changes are stored. At the end is a 2-byte checksum. It is a simple negated additive sum. It exists strictly to detect random radio frequency noise, not intentional tampering. There is no cryptographic message authentication code, nor is there a monotonic counter. Any third party can capture, forge, and replay these packets at will. Static analysis of the BAT BMS Android APK reveals exactly how the app accesses the battery's configuration memory. To write data to the system's EEPROM, the non-volatile memory that stores the safety limits, the connection must enter a specific factory mode. The app initiates this mode using a hard-coded magic value. Decompiling the code reveals that value is the plain text string 5678. DIY electric vehicle communities have known about this for years. They routinely exploit the unencrypted transport layer to swap proprietary apps for open-source tools. Relying on static magic values provides zero defense against basic static analysis. It grants any unauthenticated connection full factory privileges over the hardware. The discharge MOSFET is the physical gate keeping electricity flowing from the battery to the motor. Command hex FB sent over the Bluetooth link controls these MOSFET switches directly. Severing the discharge MOSFET physically cuts propulsion on a moving vehicle, triggering a sudden and dangerous stop in active traffic. A separate instruction, command hex FA, allows an attacker to write generic parameters. This includes overwriting the secondary hardware protection thresholds entirely. By altering calibration values, specifically a variable named temp adjust, an attacker can intentionally skew sensor readings. The battery pack will report that it is cold, even while it is overheating. When an attacker alters temperature limits, blinds the sensor readings, disables the audible warning buzzer, they create the conditions required for unmitigated thermal runaway. This vulnerability scales across the entire global light EV ecosystem. Every unit running the Shaoshang protocol shares identical GATT UUIDs, identical protocol implementations, and identical hard-coded secrets. Because the targets are uniform, a single automated script can sweep a geographic area and compromise an entire fleet. The attack requires no per-vehicle customization. Updating or patching the BAT-BMS smartphone app does not mitigate the threat. The app is merely the client. The vulnerability lives in the battery hardware accepting the commands. Remediation requires manufacturers to implement actual cryptographic authentication at the hardware and firmware level. Operation Blueshock proves that in cyber-physical systems, deploying hardware with unauthenticated digital access is functionally identical to allowing physical sabotage.